Right. Good afternoon, everyone, and welcome back to our CAWASA Wednesday webinars. We've been down for since October, I think we last met, and here we are again. And thanks to our sponsors and great coordinator of our presenters, that's Valerie Jenkinson of Operators Without Borders.
You're very
I'm
welcome, and
hoping
hello,
that
Cyprian from Bahamas. Nice to see him.
Yes. Good to welcome Cyprian, I think, for the first time. Good to have you on board and all of you.
Very long
Hopefully you
time.
had a
Hello,
good
all.
end of the year and getting all set for all the hard work around. I know this is the dry season coming up, and already a lot of our utilities are under the pressure. In St. Lucia, Wasco is now having a tariff review ongoing and has had a lot of challenges. So we're in for it. So let's see how our webinars will help us go through some of that. This evening, we have with us a distinguished guest in the person of Dr. Saad Younis Jasim. He is originally out of Baghdad University and has an MSc from University of Swansea in the UK. He is president of the Environmental Consultants of Windsor, editor-in-chief of the Ozone News International Ozone Association. And of course, he's a very well decorated professional engineer. I think you know of Walkerton, so he's a founding CEO for the Walkerton Clean Water Center following the outbreak tragedy in Walkerton, and designed successfully implemented ozone application for water reuse for greenhouse operations in Leamington, Ontario, Canada, and has supervised PhD and master's students at 3 different Canadian universities and published and presented many papers on water treatment and water quality. So we have much pleasure in welcoming Dr. Saad to our CAWASA Wednesday webinar, and I will hand over to him.
Well, good afternoon or good evening, good morning, whatever the time is, people involved. It's a great pleasure to join you in this webinar. And this is one of the topics which I consider one of the important topics in the water quality issues, which we've been working on it for more than 20 years. And it's not going to be reduced in importance because it's an ongoing problem. The chemicals of emerging concern in water and how to deal with it, how to remove it. So the chemicals and contaminants of emerging concern are, basically comprises of the groups of pharmaceuticals and different disrupting compounds or chemicals and personal care products. And those, we see it in the environment as a trace pollutants, and they are impacting the ecosystem, the drinking water, the many of the topics that would be impacting our life. And we refer to it as, for simple things rather than saying 5, 6 words, the PPCPs. And there are thousands of distinct chemicals and used in therapeutic and consumer classes. And we see it even in a small trace compounds and very widespread in the environment. And if we look at this diagram, which are produced by the US EPA, it shows that these could come from veterinary environment where people feed pharmaceuticals to their animals in order to keep them safe, don't get into disease. And I've seen in a couple of farms, they used to before inject these animals, but the thing is, when you go into a farm of more than 1,000 cows, and they start feeding it now in the water, and that water goes like in a stream, and it end up either in the sewage or in septic tanks. It depends where you are. The other one is the household. And many people, unfortunately, they get rid of the what's left over of these pharmaceuticals and they flush it in the toilet. They think that's it and done, but it's found its way to our source waters. And some people, they don't understand that, yes, it's true, we take it as part of prescription, but our body doesn't take more than 25 to 30%. It depends also on the capability of the human body. And the rest would go as a human waste. Also, where would go? Groundwater, fresh water, and also all that they find its way to the sewage treatment plants. Sewage treatment plants is a big, giant collector of these compounds. And they are not designed to remove it or degrade it. So we see a lot of these compounds go into the sewage treatment plant and end up into the freshwater sources. Also, one of the other things we see it with the climate change, the change in weather conditions, we see more storms, more precipitations, and that impacts the soil. You see more moisture, and that impacts first the freshwater sources, the surface waters, and groundwaters eventually. And that would cause deterioration for water quality and will impact eventually the drinking water treatment plants. And the problem is many of the drinking water treatment plants worldwide is downstream from other sewage treatment plants, and some of them from the city itself. And we started on these studies back in, when I used to be in Windsor. I used to be director for the water quality and production. We started in the early 2000, 2001, 2002. And at the same time, there was a big study going in the US as well. And you see here the locations. And they found these compounds in all these locations. And we were able to get funding to do the study. So we started from 2002 looking at the water quality in the Detroit River. So why these issues are of concern? They are in use in a very wide range. And the problem is the current conventional treatment plants for the sewage do not remove it. The same thing with the drinking water treatment plant. If you don't use advanced technologies, you'll end up receiving in your drinking water. And even the amount is in nanogram per liter, they are bioaccumulative and potential health effects, hormone-dependent cancers, decline in sperm counts and motility, reproductive tract disorder, and reduction in reproductive fitness. And the thing is, it's hard to measure the impact because human beings do not stay in one location all their life. And water quality changes, the food changes. It's different when you start to do a study on certain species like fish, which they have a shorter lifespan. So these compounds, as I indicated earlier, we found them in water and sediment, in wildlife, and the last one is the drinking water. And even I remember one time we had a presentation at a conference, and one medical doctor, he said, we give prescriptions and antibiotics in milligrams per liter, and you're worried about nanograms. I said, yes, but the problem is, imagine feeding babies with a combination of these compounds, a cocktail of antibiotics, hormones, lipid controls, antidepressants, and how this person system, the baby system is going to be developing, the system is developed. That's going to impact on the endocrine system. And that's why they, some of these compounds called the endocrine disrupting compounds or chemicals. And this study was done in 2003. And here what we see in this diagram, a mimic of how the disruption of the endocrine system is happening. So you have these hormone mimic will find themselves to the receptor. So either give a signal that you don't need more hormones or you need more hormones. So that will cause some disruption in the physical structure for the system and cause problems, health problems to the individual. And there are studies shows that the impact on wildlife is being now is more focused. And there are studies shows in Lake St. Clair as part of the Great Lakes in Canada, between Canada and US, they found some male fish. They start to have been developing eggs. And that's what the known name called as feminization of fish. And this gonadal intersex is suspected to have occurred from exposure to endocrine disrupting chemicals. And also other studies in the UK, in the United Kingdom, and in the United States in the 90s indicated some reproductive abnormalities in fish living below wastewater treatment plants by the discharge. And there are some studies on that. University of Waterloo, one of the professors, Mark Servos, he has in his lab 2 lines of tanks, and he starts with the fish from inception of the egg level to they grow, one with the pharmaceuticals, endocrine disruptors, and one with freshwater. And he's looking and studying the impact. It's hard to do it on a human being. You can't put someone in a lab for 30 years and find what's the impact on their body. This is what you see. It shows the impact on the male fish, and you see the male fish head start to become like a female fish as well. And see, that is what this issue is becoming a concern. And that study was done, as I indicated, in the UK and also in the North America as well. So one of the other new issues in the last 10, 15 years or so is the antibiotic resistance, or what they refer to as antimicrobial. And this is becoming a concern. And we see an outbreak in certain hospitals happening like that. The World Health Organization developed a study and collected data from 114 countries. And they look at it, this is a post-antibiotic era. And that is a concern because you have traces of these compounds are all over the place in the sewage treatment plants, and the surface water, and end up in the drinking water. A recent study about less than 2 years ago, I saw it in one of the studies in Japan. They found that the antimicrobial bacteria and genes are increasing, growing the growth in the activated sludge in the sewage treatment plants. And they looked at the impact of technologies such as ozone on the degradation and control of that growth. And what you see here is a urinary tract infection caused by E. coli, and you see a usual antibiotic take care of that, but it's not even halfway of the impact. So we talked about too many problems now. So do we have solutions? And in fact, we do. Study shows that ozone and ozone-based advanced oxidation processes, AOPs, could bring good solutions if it's implemented in the proper way and after proper study for the site. Because in everywhere you go for the drinking water or sewage treatment plants, it is a site-specific. You need to understand what is the problem facing this section or this site in order to develop the process. Because when you implement the technology, you need to look at what concentrations you're going to apply. And do you need an additional component to be added, additional chemical? What kind of a pH? What kind of organics there? All these things you have to consider. So advanced oxidation processes, the most well-known are the ozone, hydrogen peroxide, UV and hydrogen peroxide, and ozone and UV. And some they go into adding ozone, UV, and hydrogen peroxide, which is, yeah, if it depends what kind of problems you have, but that is a big operation and very expensive to operate. So we start to develop some studies on the removal of pharmaceuticals, personal care products, and endocrine disrupting compounds. And we picked the first location was in the Detroit River. One of the reasons we selected Detroit River because when you want to do a study, you want to look at the worst case scenario. Detroit River is one of the areas of concern between Canada and the United States. That's the formal title given as one of a few locations, area of concern for both countries. And because of the pollution of discharge of industries, agriculture, and all that. So we start to look into that. And also because I was there in Windsor, which we take our drinking water intake is from the Detroit River. So we started in 2002. We looked at samples collected, and we had a pilot plant we developed, and it's a dual train pilot plant. So one is a control how the current system is running, and the one which we implement the new technologies. At that time, we did not have ability to, within the University of Windsor, to implement the analysis, do the analysis. So we contacted Tulane University in New Orleans to do that. So we contracted them to do the analysis for us. So after we sent the sample, they found there are traces of sulfuric acid, bisphenol A, naproxen, and many others has been found in the raw water. So this shows that it's a concern that we need to really look at in a serious manner. And the drinking water, and that's what, in fact, the city of Windsor implemented the application of ozone in 2001, in June 2001. So we wanted to look at how would be that of effect. So the samples we took, and that was done by Tulane University in 2002, it shows there are some traces of these compounds. We found many in the, we looked at pilot plant and also full scale. So we looked at the Detroit River and we found some naproxen, sulfuric acid, as I indicated, bisphenol A, but we haven't seen much of these in the treated water after treatment. So we did another full study on that. So we looked at different months, not just one set sample. So we looked at here at the month of September 2002. We found atrazine was the biggest compound in concentration, the highest. And we found caffeine, cotinine, carbamazepine. And these compounds were very consistent. We looked at in April of 2003, and we saw a change of concentration, slightly an increase. And that's because you have more rain coming and also change of activities because of the weather. People might go out, might do more activities, and also agriculture. Atrazine is used in agriculture. Even now it's not allowed, but it has long surface life, or, like it does not decompose or degrade quickly. When we went into June, and that was the highest level, almost double the amount of atrazine we found. And these compounds also were very low. Still, there are low concentrations. So we wanted to compare how much we are doing it with ozone and without ozone, which one is more effective. That was the conclusion here in the whole data collected. And you see the yellow columns represent the removal or degradation of these compounds with ozone. And the dark navy one is the conventional treatment. And that's for the same water treated with ozone or without ozone. So you see the removal up to 100 in many of them, 100 or 90, and very high removal compared to the low removal by conventional. And then, as it mentioned, I went into Walkerton in 2005 after the outbreak. I was appointed by the government to start a new agency for the government of Ontario to train people and do research to prevent a tragedy like caused the death of 7 people in Walkerton and 2,300 people. Walkerton is a small town, 4,800 people, and as you see, location is next to Lake Huron, very cold in wintertime. Temperatures easy go -30. You could have 1 meter of snow in one night, and you know, when I went there, it wasn't an easy job because starting from scratch, an agency in a place that people died, and you need to change the image into that area for that. So, and we started, and we worked with the University of Western Ontario at that time, because that was the closest, only 2 hours away. So we developed a course on water quality, and we had the graduate students to come and get trained at the Walkerton Center. And one of the master students I co-supervised, he worked on the pharmaceuticals and removal with these technologies. So, and one of the reasons we favored that thing, because Lake Huron, you don't see many studies done there. You see, because most of universities around Lake Ontario, Lake Erie, others, and Lake Huron does not have much universities and activities and data. So that was an attractive locations to look consider. So that is at that time. So we put a tentative location for the pilot plant. And this is the pilot plant, we built it there. And you see it was a very well-developed 2 trains pilot plant. And you see here, these are glasses, the tall glasses, columns. Those are the ozone contactors. And you see here, this ozone generator, clarification units here. And here we have a reverse osmosis unit, raw water. We used to bring the raw water fresh from one of the towns on Lake Huron. They're using it. And we compare the actual treatment system with the way we are making the change. So we looked at how we treated a target turbidity 0.1 NTU, total flow. That was how much in the pilot plant, filtration rate, 10 meter per hour, coagulation dosage, 6 milligram per liter of PaCl, polymer chloride, ozone dose, very small amount, 2 to 2.3 milligram per liter, and hydrogen peroxide, 10% only, which is 0.2 milligram per liter. The gram samples were taken, and also the system, we have a SCADA that collect the data from. And what you see here, that was our master student, Mr. Faisal Rahman, and he did the study in a very, very great way. I finished his master's, then followed with PhD in Waterloo, and he's now one of the scientists working on climate change in Bangladesh. And this is the pilot plant. As we say, this is a dual train system. So this one, we added the UV in one. As you see, it's a conventional application, chemical addition, flocculation, coagulation, and sedimentation here, and goes into filtration, and then disinfection, post-secondary. We add chlorine, so we have developed like similar to a clear well. And this side, we had the one with the ozone applied. Similar to this one, no UV, but ozone. This is the ozone system connected to that side. And you see 2 columns, and we put even baffles to improve the contact and we can measure and take samples at different locations in order to see the impact of the oxidation. All this data for the ozone and all that, and the turbidity pH goes into the SCADA and collected 24 hours a day. And also we do graph sampling as well for conductivity and other water quality parameters. This is the UV system. And so these units were very helpful in doing the research and also doing the training for operators. We trained in the 5 years during my tenure there, 23,000 operators. And at that time, we had also a mobile training facility. Half of it is a lab and half is a classroom. And that goes to remote areas to do the training. So the chemicals we looked at in this one was atrazine, which is a herbicide, bisphenol A, plastic ingredients. And now this one is in Canada, Health Canada has a guideline that you don't use milk baby bottles, from plastic, because the bisphenol A will leach into the milk. So it has to be glass bottles. Naproxen, which is anti-inflammatory. Diclofenac is also analgesic. Ibuprofen is also anti-inflammatory. Gemfibrozil, lipid control. Atorvastatin, which is cholesterol reduction inhibitor. And fluoxetine, antidepressant. And carbamazepine, also an antidepressant, mood stabilization. So we looked at, and these compounds, there is a method developed done by University of Waterloo. The samples were taken there for the analysis. And so we looked at ozone and hydrogen peroxide to see the impact on the degradation of these compounds. The reaction is basically ozone, you have a direct oxidation if you use only ozone, which is the molecular ozonation. Then the indirect oxidation when you use hydrogen peroxide, the hydroxyl radical. The hydroxyl radical also very active and accelerate the concentration, the oxidation. Ozone is more selective in the oxidation. When you add hydroxyl radical, it's become more non-selective in the oxidation. And you see these are the compounds, and naproxen and atorvastatin and the others, and you see how complicated the structure of each one. And you see that's where the reaction takes place on these sides of the molecule. So it's very selective when it goes there. So it depends on that. That's why it depends. Some molecules do not get oxidized quickly because of their structure. The other ones, carbamazepine and ibuprofen, fluoxetine, and atrazine, those are slightly more complicated for the oxidation. As you could see here, it's not, you get the same oxidation thing. So the occurrence data, that is what we found already in Lake Huron. We found atrazine, carbamazepine, fluoxetine, ibuprofen, and atorvastatin. And that was the year we're doing it in. It was published 2010. We were collecting, that was about 2008 when we collected samples and doing the experiments. Here it shows what we do. We used to spike the sample because concentration is very low and you can miss it. But when you spike it, you see easier the impact afterwards. We didn't see any really much of an impact at the conventional, which only coagulation, sedimentation, and filtration. So that shows that there is not much happening when these compounds present. And that is different when we looked at the one with the ozone. and you see the one when we spiked here, and you see major reduction in some compounds. Some it did not reduced as much, like atrazine and profene and fluoxetine. And that's because of the structure of these compounds, and we only use 2 milligrams per liter. So if you want to use more, you'll have improvement in oxidation. So you see the percentage removal. You see the removal. This is the and the clarifier removal for the Saad, which has conventional only. And this is the clarifier removal for the one with the ozone. And the final one, the effluent, is that much here removal compared to this one. So a major difference. As indicated, atrazine, ibuprofen, and fluoxetine, because of the structure and the low concentration we used, we wanted to use low concentration to see, even at low concentration, how you can achieve. And one of the things we look at here is the discharges from wastewater treatment plants as well. So we start to look at some facilities that would have an impact on potential on the water sources coming to the drinking water plants. So we selected one of the sewage treatment plants in the Windsor area that would have potentially an issue compound. It's about 2-3 kilometers away from the intake. So the presence of these compounds in the environment is a growing concern. And there's a continuous load of pharmaceuticals because people don't stop taking medications winter or summer, day or night. So that's an ongoing process coming. Also, with the pharmaceutical, with the agriculture things, with the heavy rains that happens, that would leach out of the fertilizers, and also whatever is used for chemicals that goes into the river. And so that are some of the studies was done on that and shows some of these compounds, and the references are below here, a few of them, some from Canada and United States. And so it shows a lot of these compounds in the river. So the study, we looked at the Little River Pollution Control, which is on the east side of the city of Windsor. So a pilot plant was set there. This one, they use primary treatment, followed by activated sludge and secondary treatment, then seasonal UV disinfection. Secondary treated effluent before UV, we took that before to see what impact if we add ozone. So we looked at the water quality there. So we saw organics between 5 to 6 milligrams per liter, and pH was 7 to 7.2. So these are the 3 compounds we looked at: the gemfibrozole, chlorotetracycline, hydrochloride, and enrofloxacin. So these are, and there are studies done before looking at. It shows the molecular weight, pKa, and low QOWs, which helped for our study. So we found that changing ozone concentration, the ozone dose has a major impact on the degradation of these compounds. The most one impacted was the chlorotetracycline, followed by the enrocyclacine. I always forget those names. The enrofloxacin, and gemfibrozole is the slowest. And so, but still with the impact of higher ozone concentration, and you see the removal goes to below detection. And we looked at around the discharge area. The highest concentration of these compounds were around the discharge, the point of discharge, compared to further down. The groundwater was, of course, the lowest, but the highest concentration is by the discharge area. So evaluation, we looked at a further study, which was looking at different water qualities and what impact you have other parameters. And that was, in fact, a PhD study. One of our staff at the university, at the Walkerton Clean Water Center, we made arrangement and we had a partnership with the University of British Columbia, and with the so we were able to do with them a study. And one of the students, the staff, he became a PhD student, and he looked at ozone and peroxide, UV peroxide, ozone, and impact on the removal and also development of trihalomethanes, which is a concern as well if you use some of these compounds. So we looked at 3 different water qualities: surface water, which is lake current, and also a surface water, which is feeding about 7,000 people, and a goody water, which is groundwater under influence of surface water. And that shows here the experiments done on each one. It's a detailed experiment. As you know, with the PhD study, it's detailed. You need to do a lot of details to qualify the study for a PhD. So this is the water quality, and you see a major difference in alkalinity and the hardness between them, and also in the pH, and the turbidity in some of them, 0.92 to 5. So it's 5 times almost difference. And UV absorbance also, there's a difference. So that all will impact the results. We looked at the same compounds we looked at before, and we found some of these compounds in these locations. And as I indicated, that's explanation of the ones, the surface waters we looked at, and the groundwater under influence. So we looked at the removal of these compounds in the pilot plant in the conventional way only, and we saw poor removal. You see here all these compounds, and you see a very poor removal, all barely 60%, the highest, and many 10% or less even. The majority within the 30%. So that's not a good way. So comparing that, at the same time when we are looking at that, and we use the same chemicals used in the locations, these surface waters are used. So when we looked at with the ozone application, and so of course all that ozone is applied as a precoagulation and followed by the conventional, and you see with the small concentrations from 1.5 milligram per liter up to 5 milligrams, and that was used only for the sites that which has the highest organics. And so we see a very high removal. So we looked at here, and you see here, when we looked at ozone and peroxide, we saw some improvement in the removal for the same compounds. Still, we looked at a very small concentrations. If you look at ozone concentrations with the peroxide, 0.8 milligram per liter ozone, and 0.25 peroxide, even with the highest, 3.9 milligram per liter, or 4 with 0.13 or 0.02. So very low concentrations. And we saw great removal. And we saw here also ozone, and that when we looked at a higher concentrations here, 1.5 up to 5.1. So, sorry, I went backwards. So this one here, when we looked at the ozone and UV and peroxide, we saw a good removal. However, we have to use high level of energy, like 2,000 millijoules per centimeter square, and around 5 milligram per liter. And that's very high. We had previous study shows when you go that way, and that is the level required for removal of pharmaceuticals, because the level used and the regular disinfection is about 40 to 60 millijoules per centimeter square, which doesn't do anything. So they advised the manufacturer to go 1,000 plus. So we did that. We followed that. Depends on what is in the water quality. So we have that removal. However, when we look at the removal and you compare and you see ozone and conventional, it's not much different from the peroxide and ozone. So that's why when you make a decision, when you implement in your design, and you see better removal compared to the UV and peroxide with the conventional. Then here is the issue, the formation of trihalomethanes. That was the highest in the UV and peroxide. And we had a study a few years before that showed the same thing when you use peroxide and UV, because hydrogen peroxide at 5 milligram per liter or more, when you add it at the end after the treatment, because you can't add it in the pre-coagulation, because the water has to be very clear before you add it for the UV. And you see the THMs form because you have to add higher amount of chlorine, because the chlorine is reacting with the hydrogen peroxide with the chlorine. So basically, the finding was we had good results with the very effective ozone unconventional, and most effective with ozone and peroxide. Conventional is poor, ineffective. Conventional and UV and peroxide was effective, but the problem is the formation of the trihalomethanes. So these things make us to make a decision when we go for an application. Do we need to do this, and what is the end product? I went fast because of the time, to leave another 10 minutes to our questions and answers. If anybody has any question.
Right. Thank you very much, Dr. Jasim. Please, participants, do you have any questions for our learned friend? Floor is open. Yes, Valerie?
No, very, very comprehensive, and probably everybody's dazed. There's a lot of information to take in.
Yes, well, we will always have the benefit of listening again to the recording, which I will circulate promptly. I think there was something that I wanted
in the chats.
Yeah. Well, in the start, you mentioned, Doc, that there were the various levels of, I think, contaminants that may cause hormonal changes. I think you were speaking to that, and I was trying to find out, because I know there are lots of concerns now with the PFAS, etc. What sort of levels that you would have been determined that may cause some of those in drinking water that may be hazardous to?
Well, unfortunately, with all these studies we've been doing, we don't have any in the guidelines in Canada.
Okay.
The only country that has a strong regulation on these compounds is Switzerland. So they are putting guideline and regulations on the discharge and on the drinking water. And it is important. And in fact, I've been in my other role with the Ozone and News as an editor, and putting this information about these locations. And in fact, there was in the news a couple of months ago in England also, they are start to add the looking at the removal, putting it part of the guidelines, and especially One of the things, the important thing I always say, we need that for the drinking water for sure, to have like an ozone system or ozone peroxide, depends. I had one time, going back about 10 years ago or 9 years ago, I made a presentation in Europe, and the title was, "The Drinking Water Plant is the Last Line of Defense." Because if you expect everybody to follow the rules, forget it. It's not going to happen. In my role, when I was director for the Great Lakes Regional Office, we delivered 8 public meetings, 4 in Ontario and 4 in the US. In the US was Ohio and Michigan. And we warned them about the issue of the cyanobacteria. We showed them actual figures and photos, what is happening there. In 2012, nobody listened. 2014, they got hit by the outbreak of cyanobacteria. The city of Toledo, which is 500,000 people, they had to provide bottled water for about 500,000 people for 2 weeks. And also the impact of human health. We said they have to implement technologies because we have studies shows how to remove it. So, and pharmaceuticals is the same thing. Pharmaceuticals has long-term, you don't see, it's not like bacteria. And it shows within the next day somebody's going to be sick. That impacts the endocrine system and have a change maybe in years before you see a change for the person. And it depends on how old is the person, how is the health of the person to be impacted. That's why, unfortunately, we're pushing for it. Like that doesn't mean we stop. Currently, there is a plant in Montreal for the discharge, wastewater discharge sewage, the major one. City of Montreal is close to 2 million people now, and with the metropolitan area, and they're going to use ozone for the oxidation of the discharged water into the St. Lawrence River, because they saw an impact on the ecosystem and fish there. So they did studies and they looked at different technologies. They looked at ozone, UV, chlorine, and they found the best one effective without impacting these species was ozone. So pharmaceuticals, this is, how can I say, it has a more long-term impact rather than an acute impact. So that's why we have to build in our system. And I've been going to different municipalities. I make presentations to them and I tell them about that. And these seminars and webinars are a good way because we should not wait until the problem happens. Look at Walkerton. No, because people who say it will never happen here, it happened. Look at Milwaukee in 1993. They made a change and the coagulant. They didn't do it. They changed the water, look at the water source, changed that, but they didn't do a full study how would be the impact. And they end up with 100 people dead and about 400,000 sick. Then they switched into ozone afterwards. So that's why, I have a course I teach on water treatment and reuse, and I have in the course 2 items: lessons learned from outbreaks, and I put Milwaukee and Walkerton. Those 2 countries are from the G7, so people do not expect to have problems there, but we do have problems. And so you don't wait until it happens. You look at historical things, and you look at the changes in water quality in your system, in raw water. And now with the impact of climate change, you have more storms, you have major changes in water. And you heard about, in Texas a few years ago, the pipes were frozen. Who would believe in Dallas? I think it was Dallas. The pipes were frozen and broke because they don't have that system before. They don't have that weather issues. So we need to develop our ability and system to meet these problems.
Okay. Thank you for that explanation, Doc. We have a question in the chat room from Mark Lachan. Any advice for use in removal of methane and ammonia in groundwater, and in terms of cost as well, cost-wise?
With the hydrocarbon issues, it depends on the location. How much is it? So that's why I advise people before you make any suggestion. And in fact, some has used high pressure with ozone for the impact on something like that. They have done in some locations in the US. So they have some mobile units to apply that. But it's better to do a study in the location because the water quality would be an issue, and also what amount you're having and what temperature you have, because all these things will play a role. So you need to look at in the literature what is in your area, how much is the concentrations of these compounds, and where the source is to look at, because you might have other things with it as well. So that's why it's better not to give just a solution without a study. I had this situation when I went to the city of White Rock in British Columbia. I went in 2016, and they had a problem with arsenic and manganese. And I looked at what is the concentrations different times of the year. So I made a full study to look at it, to look at the speciation of the arsenic, because we found in wintertime more arsenic coming because the water is more stagnant, sticking to the geological structure. So you need to start to understand the site to make the implementation.
Okay. We have another question from Kieran Martinez. He says, once these compounds are oxidized and released into the environment, are they considered safe in the oxidized form? Also, is this process reversible? That is, can it be reduced back to the original compounds in the environment?
Usually, like these compounds, when you oxidize it, we haven't seen any. There are people studying on this. We haven't seen any real evidence about they are toxic. We know the actual ones are toxic. So we're breaking it, and you're talking about we are breaking nanogram per liter. So you break that into much smaller, oxidized. And so they haven't found any evidence. Some people, yeah, there is more toxic after that. So I said, is it more toxic than the original? And everybody was quiet. Because the thing is, when you're talking about 5 nanogram per liters broken to 1,000 pieces oxidized, the impact wouldn't be if there's any real impact. We haven't seen as I now, and scientifically, that's why Europe is still going on with it. And Europe are ahead of us, I have to admit. They are ahead of us in these studies. They started 30 years ago on these studies, and they more active in the universities on that and in the scientific centers. So, and also to reverse that, definitely not. Definitely not. To break that, when you break, you saw these molecules, when you break them, to bring them back, that will be a patent for someone if can bring them back to the same thing. I would say I'm confident that wouldn't be an issue.
Any other questions, colleagues? Feel free while you're at it. Okay, I don't seem to have any others in the chat, so I'd like to take the opportunity now to thank Dr. Saad Jasim for this very comprehensive presentation, and on and its implications in water treatment. And we hope in some other time we can have you again. We will certainly be sharing the webinar with those who may not have made it today. And we'd like to thank Operators Without Borders for helping us coordinate and finding you as our presenter. So I'm Ignatius
It's my
Jean.
pleasure. Thank you.
Thank you. I'm Ignatius Jean, the Executive Director at CAWASA. Thanking all of you for participating in this webinar number 1 for 2026. And we look forward to seeing you again next Wednesday. And if it's Wednesday, it's CAWASA Wednesday webinar. Thank you all and have a good evening.
Thank you.
Thank you.
Bye-bye.
Have a good week, everybody.
Thank you.
Bye-bye.
Bye.